Okay. Yeah, welcome everybody. This is the last session today. Last session for the barbecue and probably for the thunderstorm, or snowstorm, it's going to look like outside. This session is about Boost ASIO extensions. And when I say extensions, I mean Boost ASIO I/O objects. If you have been to the session on Monday, when Chris was talking about Boost ASIO, you maybe remember what I/O objects are. If not, no problem. We're going to look at the details now. And the idea of this session is that after the next 1.5 hours, you can add new I/O objects to Boost ASIO to call asynchronous functions, which are right now not yet supported by Boost ASIO out of the box. So that's the goal. And yeah, I have a PowerPoint presentation we will go through, and we will also look at the code in Boost ASIO. So it's not just PowerPoint only, also looking at quite a lot of code, because we have to understand how the existing I/O objects in Boost ASIO look like. Not only then, when we understand how they work and behave, only then we can do and create our own I/O objects. So that's the plan. And to make sure that we are all on the same level, let's start with a simple program. By the way, if you have any questions, just interrupt me. Don't ask too difficult questions. Chris is here, so otherwise he will correct me every 5 seconds. And yeah, if the question is too difficult, I will just forward it. Now here we have a rather simple program that uses Boost ASIO. And what this program does is uses a deadline timer. It's a class from Boost ASIO we can use. We fortunately don't need to create this class ourselves. And we can then call a function called async wait. And the idea is that you want to wait here in this example 5 seconds. And after 5 seconds, you want to be notified that the 5 seconds expired, and then we want to do something. And the trick with the asynchronous functions is that when we call async wait does not block for 5 seconds, but it returns immediately. So we can do something else until the 5 seconds expired and until the handler function is called. Now the nice thing with deadline timer is it's a class which is provided by Boost ASIO. We don't need to create it ourselves. So yeah, thank you, Chris. But there are of course other things we might want to do, not just calling async wait and waiting for 5 seconds to expire. We might want to initiate other asynchronous operations, and then we might find the classes in Boost ASIO we need.
5 seconds.
So deadline timer is just one of many classes we can use. It provides us an asynchronous function which is called async wait, and it now depends on the asynchronous functions we want to initiate, whether we find an appropriate class here in Boost ASIO and what kind of functions the classes provide us. In this case, deadline timer provides us async wait. Fortunately, there is not only deadline timer in Boost ASIO, there are a couple of more classes. You can find them all in the reference, in the documentation of Boost ASIO. Here are just some more examples. The deadline timer you just have seen. I use the deadline timer a lot in this presentation because it's a very simple class. We have something like IP TCP acceptor, which provides another function called async accept to wait for incoming TCP IP connections. IP TCP resolver to resolve host names asynchronously, IP TCP socket to read and write data asynchronously. So there are a bunch of classes we can just use where we don't need to think about how do we need to maybe implement the asynchronous function ourselves. That's the good thing. But once we want to do something else which is not provided out of the box, we have to think about how can we extend Boost ASIO and create similar classes which provide us similar functions. Oh yeah.
Back on the previous slide, previous to this. So when you construct that timer and then do the async wait, if there's a lot of things going on before you actually do the I/O service run, would the handler actually be able to be called before that time, or is it only when it's when you've done the
handler is
run?
only called when you call I/O service run.
Oh, okay.
So if you never call I/O service run, the program just terminates and there's nothing going to happen. But we are going to look at the code and maybe then it's clearer what is really going on here in ASIO. So in the session on the session on Monday when Chris was explaining the basics, we had this big cloud which he called operating system, and today we will look a little bit into this cloud and see what's really happening in BOOST ASIO. If we come back to our example, we have seen that deadline timer is just one of the many classes provided by BOOST ASIO. And these classes, they have a name, and yeah, maybe you have heard the name already on Monday. These classes are called I/O objects. And we do not only have these I/O objects in programs when we use BOOST ASIO, we always have another class called I/O service, and this class is used to create an I/O service object. So you cannot create a program with BOOST ASIO without an I/O service object. And you always need at least one I/O object, like a deadline timer, like a socket, or anything else, because only the I/O objects provide those async functions. So there is no async function in the I/O service object. Now, if you create an I/O object, like here the deadline timer, you always pass the I/O service as a first parameter to the constructor. And this is not only done with the deadline timer, but with all other I/O objects too. So the deadline timer, the I/O object, does something with the I/O service object. And we need to understand what it does, because we want to create our own I/O objects later. We will also get as a first parameter to our constructor an I/O service object. We need to figure out what's going on now. So what's really happening here is the deadline timer somehow uses the I/O service object, but in fact it is not using the I/O service object directly, but it is using an I/O service within the I/O service object. And the I/O service object does not just provide one service, but the I/O service object, here on the right side, is really a group of services, and I/O objects pick a service out of this group, the service they need. So we have really three concepts, not two. We do not only have I/O objects and I/O service objects. These are the things we see in user code. These are the things we have just seen in the sample. We have another concept, namely an I/O service, which is somehow hidden in the I/O service object. And when we create an I/O object and we pass an I/O service object to the constructor, the I/O object somehow finds an I/O service within the I/O service object and uses that service. A bit confusing because it's always called I/O service object, I/O service, I/O object. So I have to concentrate myself not to confuse you. But yeah, these are the main concepts we use here, and these are the main concepts we need to understand. And the I/O service within the I/O service object, that is really the class where the hard work is done. That's why I put the picture there. And we also need to understand how to create an I/O service ourselves and what is going on there. So it all fits together. So this is what is really going on here. Here we see the three concepts. Here we see our I/O objects, which we use in user code, like a deadline timer. Then we have an I/O service object in user code, which we always need because we pass it to the constructor. And somehow behind all of this in BOOST ASIO, we have something else called I/O services. And the I/O objects access these I/O services through the I/O service object. You also see here that different I/O objects can share an I/O service. So it's not that there's an I/O service for each and every I/O object. Here are now some classes from BOOST ASIO to make it a bit more concrete. Now here in the middle we have our one and only I/O service class. Here on the right we have our deadline timer. And the deadline timer uses the I/O service object to access a service which is called deadline timer service. We have other I/O objects like a basic stream socket or a basic socket I/O stream. Both do something with streams. And these two I/O objects, they actually access the very same I/O service which is called stream socket service. Yes?
Is the I/O service object always instantiated with the full array of I/O services?
No, it's not. These I/O services are created on demand. but we will see this. We are going to look at the code. We're going to look into IO service to see what's really happening here. Because once we want to create our own IO object and maybe our own IO service, we really need to understand what's going on here. So the IO service is really doing the hard work, and the IO service does this by calling some system functions. In the end, we have to implement something asynchronously, and if we need to call some system functions, this is really done in the IO service. And the IO service object, yeah, you can imagine it's a kind of linked list. There are a couple of services, and they are provided by the IO service object to us. And when we create the IO object, yeah, we will see this now in code. They get a reference to the respective IO service they want. Now I will look at the code, and then we get a better idea how these things look like and what we need to do to implement our own IO objects and our own IO services.
Control plus.
Is this big enough or?
Bigger, please.
Bigger, okay. Yeah, better? Yes. Ah, okay. All right. Okay, I have to scroll a bit more, but it should work. Now, these are the original sources from Boost ASIO.
What version?
What?
What version?
It is from Boost 146.1. So I think you have another latest version of
It's probably all changed.
of ASIO, but it's not yet. Okay. Now, what I'm looking at first is the deadline timer, our IO object. This is a class which is used to implement the deadline timer. And as we have seen in the sample program, I've been calling async wait. So somewhere we should expect to see a member function async wait. If I, well, jump down, fortunately I know where this function is implemented. We see here async wait. And if you look at the implementation, we see, well, there's not really much happening. When we call async wait here on the deadline timer, the function call is simply forwarded to something called service. Now, where does this service thing come from? If you look at this file and you try to find the service member variable, you don't find it here, which is no problem because our deadline timer here is inherited from another class called basic IO object, and in this parent class we will find our service member variable. It's here. So you see already later when we create our own IO object, which is just a normal class, we do the same thing as Chris did. We will derive our class from basic IO object. Now what does basic IO object do here with this member variable service? You maybe have already an idea what's going on here because I explained that IO objects, they access a service, an IO service. So somehow we get a reference here to the service we need. So let's check where service is bound. It's a reference after all. Here we have the constructor of this parent class of basic IO object. Here is our reference. Here is the IO service object from the user, that the IO service object which is created in main. And we see here that we somehow access this IO service object to get a reference to a certain service. And what is this here? There are now a couple of template parameters. IO object service is template parameter for this class. So we can check again. Here is timer service. Now here's the class we are interested in. Here is the deadline timer service. That's the class which implements the service for our deadline timer. So we somehow pass this type here to our parent class, basic IO object, which uses this type to access this service in our input in our IO service object. What's going on here with uService? What's happening here? Let's have a quick look. Here's uService. Here comes our IO service object, and we see it is accessed here. There's a member variable called service registry, And again, there's a function called useService with the type of the service. And at this point, the service registry checks whether the service already exists. If it exists already, a reference is returned to that service object. If it doesn't exist, a new service object is created. So that also means that if you have a lot of deadline timers in your program, and they all use the very same IO service object, there's only one service instantiation in this IO service object. If we quickly look at the IO service object implementation, lots of documentation, which is very good, of course. Here's our IO service class. And if we have a look what else is there defined, we have here our service registry. I don't want to get now even more into details. You see already it's a class from the detail namespace. Just think of it as a singly linked list. And here at this point, the services are kept and stored. There is not really much more going on here in the IO service, so you can really think as the IO service object as a kind of container for services. The only other member variable which you find here is this one, impl, and it somehow refers to something called impl type. And fortunately, impl type is used here somewhere in this file, so I don't need to jump around even further. Here's impl type. Impl type refers to IO service implementation in detail, and that is also here defined. Here is IO service impl detail. Here is win IOCP IO service. So we have a little bit of indirection here, but here's another class used, which is called win IOCP IO service, and this thing is somehow used together with this impl member variable. So let's see what's going on here. Where is this impl member variable, the reference actually bound? Now I have a look at the constructor of the IO service object. Here's the constructor. Here's the service registry created, which is then used to store all the services which are created on demand. Here's the simple thing. And you see there's actually the same thing happening again. The service registry is accessed. There's again useService used. And in the service registry, there's obviously another service put. And this service is then bound to this member variable just as a shortcut. But we see that we do not only have a deadline timer service, we have another service, at least on Windows, the Win IOCP IO service. Another platform, we have then obviously another class, not Win IOCP IO service. So in this small sample program we have here, where we use the deadline timer, nothing else, we have a deadline timer service for the deadline timer. But for whatever reason, we have here always, when we create an instance of our IO service object, a second service, which is also put into the service registry, but which is also accessible through that impl member variable. So what's going on there? Why do we need here a second service? The type of the second service I have just showed you, that was here Win IOCP IO service. Now you have on the one hand services which correspond to IO objects. You have a deadline, what is it called? I'm already so much confused about IO service and IO objects and everything. It's a deadline timer, and you have for the deadline timer a deadline timer service. So you have services which look toward the IO objects. But then on the other hand, as you know, maybe from the talk on Monday, the IO service is really an event loop. Somewhere deep down, there's something called like select, or in Windows, the IOCP is used. So we do not only have services which look toward the IO objects, like the deadline timer service, we also have another service which looks toward the operating system and refs, select, or IOCP. And if you think about it, it makes sense, because if you have different IO objects, like a deadline timer, like a socket, and anything else, like an acceptor or a resolver, you want to have services which correspond to these IO objects, which provide a convenient interface for these IO objects. But at the same time, you want all these services to use one event loop, like select or IOCP. And here in Boost ASIO, this event loop, select IOCP, ePOL, whatever system function is used underneath, these things are also wrapped by a service, like the Win IOCP IO service. And that means that if we just look now at the implementation of the deadline timer service, that we should find somewhere a connection to the platform-specific Win IOCP IO service. If we have a quick look at the deadline timer service, here is the class. We have seen already that our IO object, our deadline timer, simply forwards the call to async wait to the service. So somewhere we should find here again async wait. Here it is. We call async wait on the IO object. The IO object forwards async wait to the service. Then we are here. What's happening here? Async wait is again forwarded to something like service impl. Here we have the type. Okay, we have another level of indirection. There's another deadline timer service in detail. Here's again the deadline timer service. So we should again find somewhere our async wait. Here it is. Now we see there's not another call forwarded, there's now a little bit more happening. Here is now a scheduler used. The scheduler has a data type timer scheduler. And if we check what is timer scheduler, we see that on Windows it is again our Win IOCP IO service. And if we also have a look where the scheduler is a reference, is again bound. You see that here in the constructor, again, new service is used with the timer scheduler, this Win IOCP IO service on Windows, with the very same IO service object, which is passed all the way through from main, from the user. So at this point, our deadline timer service, which looks toward our deadline timer, towards the IO object, uses underneath this other second service, which is stored in the IO service object, and that on Windows now the Win IOCP IO service looking towards the operating system. So that's what's going on here. And if we want now, in a very first step, create our own IO object and reuse a service. So let's imagine we want to create our own deadline timer, or for whatever reason, Chris did not create a deadline timer, but only the deadline timer service. So just let's see how this looks like. Now this is a complete example, a complete program where I created my own IO object by reusing a service. This will be the next step. It will get more complicated if it is too boring in the moment. And if you look here at the program at main, it's actually the very same code we have seen before, except that I don't use now the deadline timer from Boost ASIO, but my own class, which I call deadline timer, to make that class look a little bit different from the deadline timer that Chris provides in Boost ASIO. I don't pass the time to wait as a parameter here to the constructor. Here I only pass the IO service object. I pass the time to wait here to async wait. Now, how does this deadline timer IO object look like? Well, it's actually pretty simple. I do the same thing as what we have just seen in code. I create a new class, derive that class from basic IO object. This is a template which wants to see which service it should use. I said that in this case I want to reuse a service. I don't want to create yet a new service. So I use here the deadline timer service from Boost ASIO. Then I need to implement, of course, a constructor, which, as all IO objects, expects an IO service object as the first, and in this case, as the only parameter. The IO service object is forwarded to the constructor of the parent class. There's not much more I need to do. You have already seen what the parent class does. And it looks up the service here, in this case the deadline timer service, in this IO service object. It has then a reference called service, which allows us to access the deadline timer service in our IO service object directly. This is exactly what we do here in async wait. We do the very same thing as the other IO object. We access service and forward the call to async wait of the service. Yes, please.
I actually wanted to ask, even earlier in the basic IO object, we have this implementation member, which kind of is not clear to me what it's for, and I now see that it's being passed as a first argument to each.
Yes, yes.
Can
That
you-
is exactly what I explained now. Yeah, that
Okay.
is also something very important. So far we have seen where the service comes from, but it's indeed right that when we look at this parent class basic IO object, which we use when we create our own IO objects, we do not only have a service, we have something else called implementation. And if you look at the IO objects here in Boost ASIO, let's have a look again at async wait, we see that not only the call is forwarded by calling async wait again on the service, we also see that this implementation thing is always passed as the first parameter to this forwarded call. Not only here for async wait, but also here for wait. Here's implementation again, and again, and again. So what is the implementation thing? If you imagine you create a couple of instances of your deadline timer, they all access the very same service instance in the IO service object. As I said, when an IO object is created, it checks, is there already a service in the IO service object? Is there already a service in this service registry? If yes, then I reuse the service. I don't create a new one. So if I have 10 deadline timers in my program, and they all use the very same IO service object and the very same service registry, there's only one instance of this deadline timer service. If I use now 10 different deadline timers and I want to wait, well, 5 seconds, 10 seconds, 20 seconds, so I want to wait different times, and they all simply call async wait on the service, how does the service know which deadline timer is calling right now? Now, one thing you could do, you could somehow pass this pointer to the service so that the service can somehow look up the deadline timer, which is right now calling. Then you need to figure out the interface. I mean, how does the service know what to look up in the IO object? So Chris turned it around and said, we have here an implementation thing in the IO object. Here's an implementation type. And the implementation type, here it is, depends on the service. If the implementation type is a part of the service and we forward everything to the service, well, the service knows the type and can look up the data in this implementation type. What does this mean now here for the deadline timer? Just to have a quick look. Where is it now? Here. Here's our deadline timer service. Here's the implementation type. And among others, I find here a member variable expiry, which contains the value like 5 seconds, so that it's clear after how many seconds, for example, the timer has to expire. Now, if you put this member variable directly into the IO object, like the deadline timer, you have to figure out, okay, how does the service know now that there's a certain member variable which stores the time until the deadline timer should expire. But as this implementation type is a part of the service, well, of course there's no problem for the service to look up the implementation type and check the expiry variable. So what we do all the time is when we forward a call to the service, we always forward that implementation thing, which is known by the service and which the service can use to find out, okay, what's going on, which deadline timer is calling right now, after how many seconds should the time expire. There's not much more to do. That's basically all. So we just derive from basic IO object, we create our constructor, we implement our functions here, like async wait, and then we just forward the call to the service. In this case it was easy because we were using a service from Boost ASIO, This is probably something you're not going to do often. As for each and every I/O service in Boost IO, there is of course already an I/O object, so it doesn't really make sense to create your own deadline timer. But this was just the first step to see how this is done. And the second step now is of course not only to create an I/O object, but also to create an I/O service. Let's jump back to the presentation to see where we are. Yeah, this is something we have just learned. The deadline timer service uses underneath a platform-specific service. On Windows, this Win IOCP I/O service. This thing is also used by other I/O services, like the Stream Socket service. And this is exactly what we want. We want one event loop. We want everybody to use this one event loop, whether it's Select or IOCP, doesn't really matter. Now, if you look at the I/O objects and at the I/O services in Boost ASIO, we see that indeed most of the classes try to use this platform-specific service underneath. But there are some exceptions, and one exception is the resolver service. The resolver service is used, well, to resolve a host name. And if you think about it, if you think about the platform-specific functions you typically call to do this, you have a function like getAddressInfo. And on the one hand, you have now this nice event loop based on Select or IOCP. On the other hand, you have a function like getAddressInfo. And then the question is, can you implement the service by integrating getAddressInfo somehow into the event loop? And in this case, it doesn't work. It works for the timer, because when you call Select, you can tell Select to return after 5 seconds. But it doesn't work with getAddressInfo. So you have some services which you cannot implement based on this platform-specific event loop. So the question is now, okay, how does the implementation look like? And we are going to check out Chris code again. Now, let's have a look at the resolver service. There's a class somewhere in Boost ASIO called resolver service, and that class is derived from resolver service base. So I'm just looking now at resolver service base, because that's where really all the details are we are interested in. So how is this asynchronous resolving function implemented if there is deep down a blocking function called getAddressInfo code? And the trick is that we have a background thread. So Chris uses here a class from Boost ASIO, but you could of course use also Boost thread. So this resolver service creates in the background a thread. I get lost here in my data. Where is it now? Here it is. Here's the constructor of the resolver service class, and here is our thread variable. When the service is created, there is no thread in the beginning, but at some point somebody will call async resolve in order to start or to initiate asynchronous resolving operation. Now somewhere we should see async resolve. Let's start there. Here it is. So the I/O object, the resolver, forwards async resolve here to our service, and now the action starts. What does async resolve do? It calls a function called start resolve op. Start resolve op first starts the thread. You have just seen the constructor doesn't start the thread yet. So here's the thread started, the background thread. And what happens here in the background thread is that we use another I/O service object and call run on this I/O service object. Now that's a bit strange. Where is this I/O service object? Here it is. That's a bit strange because we have one I/O service object in main. That's the user I/O service object. Now here in this resolver service, we create a second, I would say local I/O service object, only used here within this service. And we will call run on this I/O service object. This all happens here in start work thread with another helper class used Here is this work IO service object. I will just quickly show you that indeed run is called. Here's run called on this second local IO service object. So we have now here another second event loop going on in the resolver service. So what's happening here, or why do we need this? Let's just follow the code a little bit. Once the thread is started, we have now a background thread, and we have this IO service object in this background thread. And what we do then, we pass here, it is called operation, we pass here an operation to this background, to this second local IO service object. So what's going on here? What we want to do is we want to call get address info on the background thread. The user calls async resolve in the main thread, in main. It uses an IO object, calls async resolve, passes some data, like host name to resolve, let's say boostcon.org. And now we want to resolve the name for boostcon.org, but we want to do this in a background thread. So the service here calls a background thread, and now we need to pass the host name, like boostcon.org, somehow to the background thread. And the only reason why we use here, in this case, the IO service object is that it is very easy to pass data from one thread to another one. We just need to call here post immediate completion, which we still do in the main thread, where async resolve is called by the user. And then we pass here this operation thing. We will look at it at the next step. We pass this operation thing through the IOCP queue to the background thread, where we just called run on the other local IOCP, on the other local IO service object. So we have a second event queue, which is in a background thread. It is waiting for some data to come in. And here in the main thread, where the user called async resolve, we create something. We will have a look next. We pass this to the event queue. Then we are done in the main thread. And the background thread, where we called run, sees now that there's something to do, gets the pointer again for this operation thing, and does now something. So the only reason why we really use here the IO service object is it is really easy to pass some data from one thread to the other one. Or is there another reason, Chris?
Because you picked a version where I think I've crossed the threshold from readability performance optimization. That's no longer just the case. In earlier versions, it probably could have used the equivalent of, say, standard async, because I was just dealing in generic function objects when I passed to the background thread. The new ones, as you can see, it's passing the same object type that's queued on the way back out.
Yeah.
To minimize allocations and that sort of thing. Yeah.
Ah, okay. But in general,
the general principle stands.
yes. Yeah. Okay. Good. So far, I'm correct. Now, what's the operation thing? We still need to execute something in the background thread. So we see it is coming from whoever calls start resolve op. So just let's have a look at where start resolve op is called. Now, okay, we have here a pointer to something. You can ignore most of the things. The interesting thing is this OP thing, and OP is of type resolve op. So what is this resolve op thing again? This resolve op thing is actually a kind of function object. It is derived from a type operation. We have a lot of operations here in Boost ASIO, which are all derived from operation. And when we pass a pointer to this operation object into the IOCP queue, and on the other side, in the other thread, we get that pointer again. We will again have access to this operation. We will call this function object, not really a function object, but yeah, it works pretty similar. And we will call in the background thread do complete. And then the background thread finally will call here somehow again, and deep down in Boost ASIO, get address info. And that's now the blocking function. We are now in the background thread calling our blocking function and waiting for the host name to be resolved. At some point, this blocking function returns. And now we need to get back again from the background thread to the main thread. And in the main thread, we know that we have the IO service object by the user, which was created in main. where the user called also run in main. We make sure that we have access to this IO service object. So we access now this IO service object from the user. Again, pass here the very same operation object in which we are right now executing. You see that there is an if-else, so we can somehow differentiate if we are right now in the background thread and still have to resolve the host name, or if we have already resolved the host name, then we do what is now followed here after the else. So we just pass again here the operation thing to the IOCP queue, but this time to the IO service object of the user to make sure that now the handler of the user is again called in the main thread. I mean, the only reason why we have the background thread is we need to somehow emulate this asynchronous function. We have a blocking function, getAddressInfo. We don't want to, well, show the user that we have to call this in the background thread. The user should not care about these things. And yeah, this is how it works out. We have now a background thread. We have an IO service object in the background thread, which is calling here getAddressInfo. Once it's done, we take again this operation object. We pass a pointer now to the IOCP queue of the main IO service object. Then after some time, this function object is called again. Do complete this call again. This time we will detect, okay, we are now not in the background thread using this local IO service object of the resolver service. We are now again in the main thread, so we will execute else. And then here deep down, at this point, the user handler is executed. So the main trick here, which we have to use, is when we want to call a blocking function, which we cannot integrate into the existing event loop, like select or IOCP, we just use a background thread, call the blocking function in the background thread. If we like to, we can use a local IO service object, because it is very easy to pass something into the IO service object, so it gets out in the other thread where we call run. If you don't like to, you can of course implement it differently, but that's what's basically going on here. Now let's have a look at what our own IO object and our own IO service need to look like. Now what I did here, I created again a sample with a timer. This time I do not only want to create my own IO object, but I also want to create my own IO service object. I don't want to reuse anything from this ASIL. So let's have a look first again at this sample program. Well, it looks very similar to what we have seen before. Let's look first at my IO object. Again, it's the same thing as before. I derived this class from basic IO object. Here's my constructor, just forwarding the IO service object. Here are my two functions which I want to provide, wait and async wait. And again, I simply forward the call to service. I pass as a first parameter implementation, everything as we have seen it before. The big difference here is now we are not using the service from Boost ASIO. We are using a new service, our own service, which I called here basic timer service. Here is my basic timer service. And yeah, we have now to find out again how do I create a service. There are a couple of things I have to do again. I need to derive this basic timer service from a class called service. This class is provided by Boost ASIO. Then I also need to create a static member variable called ID. This member variable is used by Boost ASIO to find out if a service has already been instantiated and exists already in the service registry. We don't need to set this ID to any value, it just needs to exist. Well, then we create our constructor where we get the IO service object from the user, from main. It goes all the way here through the code until it arrives here. And we need it because at some point when our service finds out that the time has expired, we want to call the handler the user passed to us on this IO service object again. So we store it here somewhere in our service. And then we use the trick, which we have just seen from the resolver service. We use a background thread. And that one is here. Here is the background thread. In this case, I use toThread. And I also use a local IO service object because it is so easy to pass data from one thread to the other one. That one is here, my local IO service object. And of course I call then again here at this point run on this IO service object in the background thread. So the event loop is started. It is not waiting for some data to come in. But the problem is if I start now the thread here and call run, there's nothing to do right now. There's no data coming in the event loop. So run would return immediately. And Chris mentioned also on Monday that if you want to make sure that run does not return when there's nothing to do, you create a work object. There's another class here in Boost ASIO which is simply called work. Here it is. And if you use an object of type work and you bind it here to an IO service object, run does not return, even though there's right now nothing to do in the event loop. So now we set up our background thread, we set up our IO service object, and now we can call our asynchronous function. Now here's now async wait. No? I always forward async wait from my IO object to the service. And what I want to do now, I want to call a blocking function. I want to wait, for example, 5 seconds. I want to do the very same thing as the resolver just did. So I want to pass now the data I get from the user, like a number, like 5 seconds, to the background thread. So I can call a blocking function and wait 5 seconds. Now I set up everything already. I have my background thread, I have my local IO service object. The only thing I need to do now, I have to pass a function object to this background thread, to my local IO service object. For that I have created a new class here, a wait operation. Here it is. As you see, this is really a perfect function object. And I put in here a couple of data. Among others, I have of course to put in here the seconds, so that the background thread knows, well, for how many seconds it should call the blocking function. So at this point I have now a function object and I pass it through post from the main thread. Async wait is called in the main thread. I pass this function object through post to the local IO service object. This is the local IO service object which I have created here in my service. And as I have called run on this local IO service object in our background thread, the background thread gets now this function object and will execute it. So yeah, again, shows how easy it is to pass data from one thread to the other one through the IO service object. Now what's going on here? I've passed a little bit of data here, like the 5 seconds. Here's now my overloaded operator. And the only thing I need to do then, I call here wait on my implementation. Now that's the last thing we have to look at. There's not only an IO object, there's not only an IO service, there's of course also this implementation thing. Here's the implementation type. In this case, I use a shared pointer based here on this type timer implementation. And this is now the last class to look at. Here's my timer implementation, and it really doesn't do much. It has only a wait function, and it uses here, it's now Windows code only, uses here a wait for single object call. This is the blocking call. Here I want to block now, for example, for 5 seconds, and because I have now a blocking call, I need the background thread to do this. When a new IO object is created, we have seen this here. Where is it now? Then the constructor of our parent class basic IO object is called. We have seen that we get then somehow reference to the service, but there's something more happening. There's also construct and destroy called on the service. So the implementation is passed to the service in case the service needs to initialize something or needs to clean up. And in this case, I have of course also to implement construct and destroy. And what I do here, as my implementation type is a shared pointer, well, I just create an instance of this shared point of this timer implementation. put it here into the shared pointer, and in destroy, I reset the shared pointer. Why do I use a shared pointer here? Think about the following. When I create my I/O object and I initialize my async wait operation, I pass some data to the background thread. So at some point the background thread will pick up the data, call the blocking function, and maybe call my handler. But what is of course theoretically possible, that my I/O object goes out of scope before the handler is called, before something is done in the background thread. If my I/O object goes out of scope at this point, destroy is called, and destroy here, as we have now seen, will, where is it? Here, will also destroy my timer implementation. Will reset my shared pointer. I mean, that's the idea. That's actually what I want to happen. If my I/O object doesn't exist anymore, I don't need the implementation data anymore. But that's a problem once the wait operation, once the function object is executed, because that one has of course access to the implementation. It needs to find out, for example, how many seconds it should wait. And yeah, it's I guess coincidence that all the sessions today are about concurrency. But in this case, I use a shared pointer here and a weak pointer in my function objects to synchronize these two threads somehow. I'm not sure if you have seen this before, shared pointer and weak pointer. So for those who haven't seen this, quick explanation. Now if in my background thread this operator here is called and the background thread decides it wants to wait now 5 seconds, it first tries to see whether this implementation object still exists. So it accesses this weak pointer, and if the implementation object hasn't been destroyed yet, which means the I/O object did not yet go out of scope, it gets a shared pointer, and if it has a shared pointer, everything is fine, and it can call wait. And if the I/O object goes then out of scope, it's not a problem because I have my shared pointer here. If the I/O object goes out of scope, while I'm right now trying to access the implementation object, and it is gone before I can call lock, I get an empty shared pointer. So I see at this point, okay, the implementation object doesn't exist anymore, so I better don't try to wait and I don't try to access it. I simply call the handler of the user immediately with operation aborted. The last thing, then you have really an idea how this whole example works. What happens if I call wait, and I wait now 5 seconds, and then at that time my I/O object goes out of scope, and I don't have any implementation thing anymore. Well, the implementation is still there because I have a shared pointer. That's fine, but I don't want the operation to continue because my I/O object is gone. That's why I call here in destroy just before my implementation is resetted. Destroy on my implementation. Here's destroy, and in this case I set an event. So this is now Windows specific, and if I call this set event on this handle, which is used here, wait for single object returns immediately, and I can see here when I check the return type that wait for single object did not return because the time expired, but yeah, because I interrupted the asynchronous operation. In this case, I again set this error code operation aborted. This is passed here through the reference to here at this point to my function object, and yeah, then again at this point I call the handler of the user, and the handler of the user will see operation aborted. So it's not that difficult to implement all of this. You just need a background thread if you have a blocking function. But yeah, as is typical for concurrency and multi-threading, you have to figure out how to make sure what happens when your I/O object goes out of scope, if that really still works as you have planned.
Thanks, Scott.
Yes.
One minor quibble, and that's the stuff that's in the destructor where you're joining the thread. The service destructor should be in the shutdown service function.
Okay. I explained that we need a construct in the destroy because we have seen this is called by a basic I/O object, and we also need a shutdown service. It's again something which is called somehow by BusASIO, and if I understood now correctly what Chris just said, the code which I put here into the destructor, So these 3 lines, they should be put down into shutdown service. Okay. So I can actually just upload all the files to the website. I guess we have this collection of PowerPoint presentations and PDF files. So if somebody wants to use it as a template to play around with it, yeah, it's then all there, so you don't need to type it now.
2 questions.
Yes.
Should this be private, shutdown service?
Yes, it can be private, right?
Yeah, it's a virtual function, so
Oh, it's okay. All right. So now, okay. All right. Second.
Ah, okay.
Um,
Marshall said that it's a different camera, but we don't need a micro. I think so. We all speak loud enough.
Speak clearly.
Sorry. Second question is, so in this case, when the object went out of scope, because it's an interruptible process, as it were, it is a design choice to say set aborted, right?
Yes. Yes.
You can make the design choice not to abort it.
Yes. Absolutely.
Okay. Nothing is forced on by yourself.
Yes. Yeah. You can design it the way you like. Yes. So it would be indeed easier if you don't want to interrupt it and you just wait 5 seconds.
Yeah. If it's a long-running computation and I just call LAMAC or whatever external library, which is running a whole bunch of computation, I usually can't do.
Yes. Yeah. Absolutely. Yeah. Now, if we jump back to the presentation, we have now seen the second possibility to implement a Boost ASIO extension. The first one was really simple, just reusing a service. The second one was now a bit more realistic, creating an IO object and then creating a corresponding IO service. So we have seen it all looks now a little bit like this. We have now IO objects which use IO services, which again use underneath the platform-specific IO service, and we have other IO objects like the basic resolver in Boost ASIO, which uses a resolver service, which uses a background thread. And there's a third way to create, and the last way to create an IO object, which is using the class WinIOCP IO service directly. So if you know you have now, you want to call a function, you know that function can be somehow used together with IOCP, you might want to use the class WinIOCP IO service directly. And we will now look at an example where I wanted to create a directory monitor. So I wanted to watch a directory and see if another process creates a file or if a user changes a file, and then I want it to be notified. And I can call a function on Windows, which I can somehow use together with IOCP. And I had created a normal service like this one, which would then use WinIOCP IO service. And I had sent in the email to Chris to ask if everything is fine. And he said, it's not a good idea because WinIOCP IO service is in the detail namespace. So you really shouldn't use any code from detail. So all the other services which are provided by Boost ASIO, you just use this class, but you better don't do this yourself. Now fortunately there is a class in Boost ASIO which is called Boost ASIO Windows Overlap Pointer, which is a kind of extension mechanism to access this class in the detail namespace, which you shouldn't access directly. And with this little helper class, you can indeed use this IOCP event queue from your own code without using code in the detail namespace. Now let's have a look at this last example. This is now a directory monitor to watch whether there's anything going to happen in a directory. And let's have a look again first at main. So here's my directory monitor, my IO object. Again, I pass my IO service object as the first parameter. Here's the path to the directory I'm interested in. In this case, it's the local the current working directory. Then I call async wait. I want to be notified if something happens in this directory, if a file is created, updated, or deleted. And then I want this wait handler to be called. This wait handler does not only tell me whether everything worked out, there's always this error code passed. It also gives me a little bit more information, like an action code. I was just passing through the data I get from Windows. That is a number which tells me whether something was created, changed, or deleted. And I also get then here a path, so I know, which file was actually modified. Yeah, and then I call run again, and I expect it should all work out of the box. Now, this time here, I'm lucky because I don't need to call a blocking function. On Windows, yeah, maybe you know, there's a function called read directory changes W, and this function can be used somehow together with IOCP. And we know now that there is in Booz Azure this IOCP service. So we want now to put everything together. We don't want to access this IOCP class directly, as we have seen it is in the detail namespace. So we want to use the overlap pointer somehow. But let's have a look at this IO object. Now it turns out that this is actually rather easy. You see, it's just a normal class. We don't need to derive it from anything. I have created here my constructor. As usual, the first parameter is my IO service object. And what do I do then? I have to open a handle for the directory I'm interested in, which I want to watch on Windows. I do this here with create file W. It's all Windows specific. Then I store the handle here in a member variable. Yeah, that's actually all. More I don't do at this point. Continue then when somebody calls async wait. At that point I really want to watch the directory and see what is going to happen. And now I use this overlap pointer class from Booz Azure, which helps me to access the IOCP service Booz Azure provides. So what do I do here? I create an object of type overlap pointer. I need to bind this object to the IO service of the user, because that is the IO service which is later used to call the handler again. And I also pass here a second parameter, which is in this case something of type waitOp, and waitOp is defined here, and it's again function object. This waitOp is the thing which should be called when the asynchronous operation is complete. When IOCP sees that read directory changes W got some data. So when I have now created my, when I have now created my overlap pointer, I initiate the Windows asynchronous operation with read directory changes W. On Windows we have then to pass kind of certain special structure, it's called overlapped, to these kind of functions. So I can get this Windows specific structure by just calling get on my overlap pointer. At that point, Windows understands it should not block read directory changes W. It knows now that an asynchronous Windows operation is initiated, and read directory changes W returns immediately. If there's an error, we simply call complete on this overlap pointer with the error code, and complete means that the handler should be called immediately. There's no need to wait now for this Windows asynchronous operation to complete because we got an error. If we didn't get an error, we don't call complete but release, which means we pass now the information and everything, the execution, to the underlying Windows specific IOCP service, and at that point we are done. We passed now here in this case, for example, here it is, the wait operation, the function object, into the IOCP queue. That's how you can imagine it. And now the IOCP queue is waiting for read directory changes W to complete. That's the Windows specific asynchronous operation. And at some point, we see that there's some data coming in. We see something has happened in the directory which we are watching. And then again, Booz Azure takes over. It does something a little bit. And at some point, it calls then our waitOp function object. So when waitOp or waitOp function object is called here, we know the Windows specific asynchronous operation has completed, and read directory changes W got now some data which we can now interpret here to find out what has actually happened, and then we can call also the handler of the user. Now this structure waitOp has two member variables. The one thing is the handler of the user. After all, we need to know what thing we need to call. So we see when we create our object of type wait up here, we pass the handler which is provided by the user here into this object. We need this later when we know the Windows specific asynchronous operation is complete. And what we also need, we need some buffer. We need to provide some space so that read directory changes W can put the data somewhere it gets from the operating system when it sees something has happened in the directory. This is how read directory changes W works. It wants to get a little bit of space to put in the data, which we will use then to interpret and understand whether a file was created, deleted, modified, whatever. This is all put here into this wait op object because we need all this data later then when this asynchronous operation is complete. We need to call the handler, of course, and we need to interpret the data in the buffer. This is exactly what we do here in this operator. If we got some data, we are looking into the buffer. We have to cast a little bit the pointers, and this is all Windows specific. And when everything works out, we call here the handler with the data the user is interested in. At that point, we are back in our program here below and can here, for example, just print the data to the screen. Yes?
Up in there, what were you doing with the handle? It seemed to be Windows native, but also ASIO specific.
Which handler do you mean?
Handle. All right, now scroll up a bit.
Okay.
Overlap thing.
Yeah, so when you give it to overlap, on the handle you get the I/O services, but when you give it to the Windows API, you give it to native. What's going on with that?
Yeah, as far as I understand, please correct me, Chris. Oh, you want to answer?
Okay. Yeah, so there are a couple of classes in ASIO for wrapping Windows handles.
Oh.
So this
Okay.
As far as I understand, it's just an utility class, right? We could implement the same program without using the handle class from who's ASIO here.
Yeah.
We would need to store.
No, the one thing it does that you can't do is it registers with the underlying IOCP I/O service for you.
Okay.
So it accesses the detail namespace to do the necessary registration.
Okay. So that means we really have to use the class
For
here. Right?
that purpose, yes.
Okay. Okay. So this handle thing, which is used here, is based on class stream handle, which is also provided by who's ASIO.
So as a user of this class, I could just view it as a handle that'll work both for ASIO and Windows.
Yes. If you call the native function, then you can pass it to any old Windows API call.
So this is really the last picture. This is, as far as I can tell, what we can do to extend with ASIO. The first thing what we did, we reused the service. This was pretty simple. And probably something you're not going to do often in practice is, why should you reuse a service if for each and every service you have already an I/O object? The second thing, when you need to create your own service, you do this when you have to call a blocking function to simulate an asynchronous operation. And the third thing which we just did is you know that you want to access a platform-specific service like WinIOCP I/O service. You cannot or you don't want to access the class directly because it's all in the detail namespace. There are, of course, other classes for the other platforms which use then selects or equal or anything else. And for that you have then fortunately classes like overlap pointer which provide you indirectly access to these platform-specific services. So I can all put the code to the website. We can all upload the code to whosgone.org. So if you really want to play around with it, that you can easily check it out. And if there are any other questions, just ask me, or even better, Chris. Yes.
So when you create this new service, typically you're passing some data to it, right? So in your deadline timer class, you passed 5 seconds or whatever it is that you passed. So it's generally passed by value so that the new service, when it passes to the service object, it retains a copy of it, right?
Yes. Yeah.
All right. So do you have any advice on? So typically, what we the kind of application that I'm thinking of is, let's say I have lots of computations to do, and I have huge matrices that I need to do something with. And I have a bunch of graphics processors on my computer, and I can pass a whole bunch of stuff to do in parallel. So the copying the data itself is a potentially expensive operation, right? So is there I don't know how to phrase this. Is there a standard paradigm, standard way that you deal with passing large quantities of data, or is it just create a shared array? And
I might answer this way. It's exactly equivalent to performing an I/O operation like a read or a write on a socket. You have a responsibility to make sure the buffer in that case is valid until the operation completes. So you don't have to necessarily copy your argument, provided you can make that guarantee that you will not destroy your matrix until the expensive operation calls you back in the handler.
Okay, in practice, that typically means either it's with the same scope, but you created it earlier, or you have a shared pointer or something.
Well,
no?
how you do it is your business. But just that you ensure that the lifetime is long enough.
Okay.
He's not going to tell you how to design it. So again, with the shared pointer, it's pretty simple.
Yeah, so the only question is, think of partitioning it into two parts, right? So there is some work, copying or whatever it is to set up this stuff for lifetime management in your bottom, in your boxes at the bottom row. And then the rest of the work actually happens in parallel. So I was trying to figure out how much of it needs to be.
I don't think there's a general answer. It really comes down to how you implement the iObject in the service.
Okay.
I think what I've just done with the checkpoint is something easy to do, or at least try to keep the code simple. But whether this makes sense in your application or in your use case, it really depends.
If I can just add that you'd only really be writing a new service for this if there is some resource that should be shared across the I/O objects that you're layering on top. So in this case, there's the background thread to do the work. That is the shared resource. If you have some other way, so analogous to the directory changes thing, another way of doing the asynchronous operation that doesn't mean a shared resource between all of your objects, then you don't have to use a service for that.
Like in the last example where we just had one
Exactly,
class, right?
exactly.
Yeah.
So, yeah,
Typically with the kind of things I'm thinking of, I only have a limited number of graphics processors on my
right. So if there's a shared resource, then yes, a service would make sense in that case.
All right. Any more questions? Good. I think then we can all create now lots of IO objects, and then a lot of emails to Chris. With age, it grows and grows and grows. Okay. Thank you.